Hello, Mohammed, and I will present you today our recent work, Better GPU Hash Tables. And we did this work with my co-authors, Saman and Serpan, Martin, and John. So first, let me tell you a little bit about me. I have a bachelor degree from a very different field, naval architecture and marine engineering. I got my bachelor degree from Alexandria University back home in Egypt. And I started learning about problems like mesh generation, point sampling, and I learned about CUDA back then. And I joined UC Davis back in 2016, and I started my PhD in the electrical and computer engineering department. And I'm working with Professor John Owens. And my main research interests are I mainly focus on concurrent data structures. So how to design a data structure that supports concurrent operations such as insertions and query operations. And I show you here on the left a recent work that we did, which was designing a B tree. And on the right, something that we are currently working on, which is a data structure that supports multi-versioning. So you can do this on the device or host, and it's a very powerful technique, and you can implement very powerful things with it. So I'm very excited for the future of this research in the next few years, because I think we can do a lot of powerful things. But today I would like to talk to you about hash tables. So we have a specific problem, which is building a static hash table and querying the hash table. And we would like to discuss what are the factors affecting the performance and how we design these hash tables. So first, let me start with defining the problem and giving you a very simple example for building a hash table. So we have a hash table data structure that will occupy a space M, and this is the only space that we will use. So we will not use any other space. And we would like to insert a number of keys N into this hash table, and we would like to ask a few questions. What can we perform the insertion, yes or no? And this insertion given N keys, it will define the load factor, which is N over M. And if we can do the insertion, how fast can we perform the insertion? How fast can we do the query? And we care about the different scenarios of query operation. So for example, queries could exist on the hash table, so they are all positive, or they do not exist in the hash table, so they are negative, or we have a mix of both. So let's look at a very simple hash table first. What we did here is that I took the space and I divided into slots where each slot can hold a key or a pair. And I will use the term key or pair interchangeably. And at least when the pair size is less than 8, they should be the same. Is less than 8 bytes, they should be the same. And we need a hash function. So this is a hash function that we will use in this example, and we will use throughout our paper and the rest of this talk. And let's try to insert a key. So we try to insert key A, and the hash function will map this key into one of these locations, and the performance and the insertion will succeed. So notice here that we only needed to do a single memory operation to perform the insertion. So we care about this memory. We care about this count. And let's try to do another insertion. Again, a single probe, another insertion, again, a single probe. And finally, this insertion hit a collision, meaning that we try to insert into location that is already occupied. So one easy solution is just let's try to find the next empty location and insert the key there. So we will try the next location. It's occupied, so we can't use it. We'll try the next one, so we will insert over there. And here we see that it took us 3 probes or 3 memory accesses to perform the insertion. So memory bandwidth is a very precious resource on the GPU, and hence we care a lot about how many probes we perform. So any hash table design, we really need to focus and understand very well how the hash table how the hash table design affects these number of probes. So I will discuss with you how the different design decisions that we can make affect the number of probes that the hash table will do or will perform for either insertions or queries. So we have a few design decisions to make, and I listed them here. So first, the probing scheme. For example, the one I used earlier in the example was linear probing. But today I highlighted the one that I will discuss today in this talk, and the one that we discussed in the paper, which is Cuckoo hashing, bar of two choices, and Iceberg. And we have another design decision, which is the bucket size, meaning that you can divide the hash table into buckets. So what is the bucket size that we should pick? And this is the only design decision that the hardware will constrain us to. The hardware will tell us, or to optimize for memory access, the hardware will pick the bucket size for us. However, we can still change its number if we really want to. And another design decision is probe complexity, meaning that how many hash functions that we will use. So you can use 1, 2, 3, however many that you want, but they will affect performance. And we will see how the probe complexity affects the performance. And finally, if we have multiple hash functions, this means that we have choices. So each hash function will map to a bucket, and we need to decide on a placement strategy. For example, a balance technique where we try to balance the load between the choices that we have or the hash functions that we have, or maybe not a balance technique. And we will see how this placement strategy affect the performance. So next, I will discuss all of these design decisions, and then we will look at the results and how they affect performance. So first, probing scheme. Let's first discuss Cuckoo hashing. So again, so let's assume here that I'm using two hash functions. And first, let's try to insert A, and I will always try to use a hash function on the left to perform the insertion. So I will always use this hash function to perform the first insertion. So key A will map to this bucket, and we will perform the insertion. And then I inserted B and C in the same manner. And now let's try to insert the key D that will cause a collision. So we can't really insert D because this space is occupied. So what Cuckoo hashing scheme does to resolve collision is that you exchange the key you're trying to insert with the key that occupies the place. So we exchange D with B. And now we inserted D, but we try to reinsert B. And here we go back to the two hash functions, and we evaluate the, the two hash functions for the key B. And then we will use a round robin scheme to determine which hash function to use. So by evaluating the two hash functions, we can tell that we kicked the key B from this location. So we're not going to use this hash function, and instead we will use the second hash function, and we will perform the insertion. And obviously this can go on for more than an iteration, but that's basically the same as idea. And if you want to do a query operation, it's basically the same. You first use the first hash function, look at the bucket. If you find the key, then you're done. If the key does not exist, you can terminate. And you only can terminate because remember, I was always using the hash function on the left to perform the insertion. So that's why I can terminate early. However, if you don't find the key and the bucket is not empty, then you must check the second hash function. Now, the second probing scheme is power of two or more choices. And in this example, I divided the hash table into buckets. So each bucket has a capacity or a size of 2. And again, I'm using two hash function. And the idea behind power of two hashing is that you are trying to balance the load between the buckets. So given two hash functions, you evaluate the load of the two buckets that these hash function points to, and you try to insert into the bucket that is least loaded. So for example, key C here maps to the hash function will map to these two buckets, and bucket 3 has a lower load than bucket 2, so we will perform the insertion in bucket 3. So we expect this to achieve high load factors, and in general, you can use this technique to you can combine this technique with other techniques. For example, you can combine it with Cuckoo hashing as well. However, the problem here is that you require at least 2 probes to perform the insertion. So remember here, I had to evaluate the load as the 2 buckets. So we have to do at least 2 probes. Similarly, for queries, if you want to do a query, then you have to evaluate the 2 hash function, because you can't really do because you can't do an early termination. You must evaluate the 2 hash functions unless you find the key in the first bucket. Now, another technique, a recent one, is Iceberg hashing. And the key idea behind Iceberg hashing is that you are trying to optimize for the common case. So the common case is that you will try to insert the key into a bucket and you will succeed from the first try. So let's try to optimize for that. And we optimize for that by using an additional hash function, and we call it a primary hash function. And we have the 2 secondary hash functions as well. So how does insertion work? To perform an insertion, you first evaluate the primary hash function and you compute the load of the primary bucket. And if the load is less than some threshold, you perform the insertion into the primary bucket. And if it's not, then you use a different technique to perform the insertion. So you do more effort to perform the insertion in this stage. So for example, you could use power of 2 hashing, and then you will have to evaluate the 2 buckets and their load and insert in the least loaded bucket. For queries, you do the same thing. You first evaluate the first hash function, and if you find the key, you're done. If you don't find the key, then you must check the 2 other buckets before you can terminate and decide if you found the key or not. So you can see here that the number of probes for this technique is something between 1 and 3. 1 if we succeed from the first try, and we're hoping that this will be the common case. And in the worst case, we will do 3 probes. So I gave you a brief overview of the different probing schemes, and then I will show you very quickly how the bucket size affect the number of probes that the hash table uses. So here I'm showing you this figure, and the source from this figure is this PhD dissertation, which I highly recommend reading. I think it's very well written. So in this example, we have a Cuckoo hash table that uses 2 hash function, and we are changing the bucket size between 1 and 6. And you can see here the power of increasing the bucket size. So once you increase the bucket size from 1 to 2, the load factor that you can achieve goes up from 0.5 to around 0.9. So increasing the bucket size is very powerful to achieve higher load factors. However, like we mentioned, you don't really want a bucket size of 2 on the GPU. You want a bucket size to match the cache line. So for example, an optimal bucket size would be 128 bytes, which will be 16 key value pairs if the key value pair total size is 8 bytes. And now for probe complexity, which means the number of hash functions, here we can see how the effect of increasing the number of hash functions. And you can see here again that increasing the hash function improves the load factor. So for example, if you increase the number of hash function between 2 to 4, you can increase the bucket you can increase the load factor from 0.5 to 0.9. So combining increasing the bucket size and the number of hash functions that you can use will typically improve the load factor that you can achieve. However, they affect the performance in different ways, and we will see how they affect the performance. Finally, the placement strategy, which is something that I showed you earlier in power of 2 choices, for example, a balanced or not balanced technique. And I told you that if you decide to do it in a balanced way, you will achieve higher load factors, but it will cost you to achieve higher load factors because you will need to perform more probes. And if you don't pick a balanced technique, for example, like when I did for Cuckoo hashing, we just we saw how fast we saw that we can terminate early during queries, which we'll see that is very powerful in specific workloads. So we talked about the general design decision. Now I have only, this is the only, I will discuss a specific part of the implementation. And I'm not going to discuss how to implement the different probing schemes, but I will tell you about the most important piece when we try to implement an efficient data structure on the GPU. So in general, what we want is we would like to avoid branch divergence, and we would like to achieve a colorless memory access. And we can do this by this technique, which was the main idea of thesis of or dissertation of Saman, my co-author, and it's becoming the norm now to use this technique to implement any data structure. So I'm showing you here an example where we are trying to perform an insertion in a cooperative fashion, and every thread has its own assignment. So thread 0 is trying to insert A, thread 1 is trying to insert B, and so on. So what we will do is that we will construct a tile, and we're using here CUDA's cooperative group. And in this example, I'm just using a tile size of 4. And how we do the insertion, or how we perform the operation or do the insertion in this example, is that you serialize the operations between inside the tile. So first you insert A, then you insert B, you insert C, and then you insert D. And that's basically the main idea that you need to, the main idea behind this cooperative strategy. And insertion could be an insertion, or it could be a different whatever operation, for example, a query. And the details of the implementation of this operation is straightforward, and it's too easy to write. We pretty much wrote the whole implementation inside the paper as well. So now I will show you some results. So first, I will tell you that this is the efficient way to implement the data structure. And so let's see how well we did in these figures. So in these figures, in the left figure, I am measuring the DRAM sectors per key insertion. So sector is 1/4 of a cache line, and we are measuring this number using the profiling tools. And on the right, I'm showing you the achieved DRAM throughput. And these experiments was, we ran this experiment on a Titan vGPU, which had a peak bandwidth of 652 gigabytes per second. And I show you here the different techniques. For example, the first one is a Cuckoo hash table with bucket size of 1, bucketed power of 2 Cuckoo hash table, bucketed power of 2 hash table that uses a bucket size of 16, and a bucketed Cuckoo hash table that uses a bucket size of 16, and one Cuckoo hash table, which is a Cuckoo hash table that uses 4 hash functions and a bucket size of 1. So I will discuss 2 of these curves. The first one is 1 Cuckoo hash table. So remember that this hash table uses a bucket size of 1, and you can see here that and you can see, for example, for insertion, the purple line, you can see here that we at least need to touch 4 sectors to perform an insertion. And at higher load factors, it goes all the way up to 7. So 4 sector is basically what we need, because we actually need 4 hash functions. So, and even at low load factors, we need at least 4 sectors. But the key important thing here is the DRAM throughput. As I mentioned, that this hash table uses a bucket size of 1, so it's not very efficient to use this technique on a GPU, because again, we would like to utilize the entire cache line. And you can see here that it only achieves around 150 gigabyte per second. Now let's look at a different technique, and in general, bucketed techniques that have a bucket size, in this example 16, will work very well, because a bucket size of 16 means that we are effectively utilizing the cache line. So let's look at, for example, at bucketed Cuckoo hash table, which is the green one. And you can see here that at low load factors, you require a little bit more than 5 sectors to perform a single insertion. And at very high load factors, you need around 6 sectors to perform the insertion. So this is very powerful. Six sectors per insertion, meaning that you are touching 1.5 cache line to perform a single insertion. So imagine you're inserting a key at very high load factors, and you only need 1.5 memory accesses to perform the insertion. So this technique is very hard to beat because of this. It's a number of probes or the number of memory transfers that you need to perform. And you can see here on the right, you can see how well it performs for queries. So during queries, like all of these are bucketed techniques. So all of the dotted lines here are bucketed techniques, and you can see how well they perform because they effectively utilize memory as a cache line. For insertion, it's a little bit different because there are atomics involved in the operation. But again, it's better than one Cuckoo hash table. So this figure is not in the paper, but I show you. But I have it here to show you that the effect of changing the number of hash functions on bucketed Cuckoo hash table in implementation. Like from the implementation, the figure that I showed you earlier was from theoretical experiments. And again, it's really about the number of probes. Number of probes is the most important thing that we need to care about. And let's look for so on the left, I'm showing you the number of probes. So we count the number of probes that the hash table operation performs. And on the right, I'm showing you the insertion, the search throughput. So let's look at 3 examples. One is a bucketed Cuckoo hash table that uses a bucket size of 8 and 2 hash function. Blue one uses 3 hash function. Green one uses 4 hash function. And let's look at how the number of hash function changes the load factor. So you can see here the red curve using 2 hash function. You can see that once we increase the hash function, the number of hash function by 2, the number of probes, it increases, but we can achieve higher load factors. And similarly, if we increase the number of hash functions again, you will increase the number of probes, but you will achieve higher load factors. You can see here that increasing the number of hash functions, it improves the load factor. However, if we look on the right, again, we're looking at the red line, 2 hash functions, blue line, 3 hash functions, green line, 4 hash functions. You can see here that increasing the number of probes or increasing the number of hash function, it increases the load factor, the achievable load factor. However, it reduces throughput that you can achieve. So there is this trade-off between how much load, what is the load factors that you are really trying to achieve versus throughput that you are getting back, at least for this example, the search rate. And I will tell you later about how it affects the other parameters or the other performance criteria. So now I will go over the different techniques that we mentioned, the different probing schemes that we mentioned, and in the end, I will summarize with a comparison between all of the different techniques. So I will highlight the important things here. So this is an insertion operation. Again, on the left, I'm counting the number of probes per key. On the right, I'm showing you the insertion rate. And you can see here that a Cuckoo hash table that uses a bucket size of 1, it requires a lot of probes to perform the insertion, and it goes all the way up to around 3. However, you can see here the power of bucketed techniques. You can see that bucketing, it really improves the number of probes that you need to perform. And again, you need, for example, for a bucket size of 16, you need around 1.4 probe to perform an insertion. Again, this is the power of Cuckoo hashing. You need very few number of probes to perform an insertion. And on the other side, like on the right figure, you can see the insertion rate. Again, you can see the power of bucketed techniques in general. And you can see here that when the bucket size is 16, which matches cache line perfectly, you get the best performance. So it's clear from here, from these figures, that we want a bucket technique and we want a bucket size of size 16. For both subqueries, the results are similar. Bucketed techniques outperforms not bucketed techniques, and a bucket size of 16 outperforms all of the rest of the techniques. Now, negative queries is a very interesting workload because like you can see here how many hash functions that we are using. Because what happens is that you need to look at all possible locations, or you need to inspect all of the buckets mapped by the hash functions. So for example, in the worst case, you're not finding any keys, but you have to check all of the buckets, and you can see at very high load factor, all of the bucket techniques converge to somewhere around three probes, which is equivalent to the number of hash function 3. And on the right, you can see how the performance looks like for these operations. Again, bucketed Cuckoo hash table with bucket size 16 outperform the rest, but you can see here that they all converge to a similar performance when at high load factor, because you need to touch all of the possible buckets that you can hash the key into. Now, for a bucketed power of 2 hash table, this one is straightforward. Remember, we always need to do 2 probes per operation. So to perform an insertion and you're using 2 choices, you have to evaluate the hash function at the 2 location, and you have to compute the load for the 2 buckets. So you have to perform 2 probes. And this is how the performance looks like for insertion. And we show here 2 different bucket sizes. So bucket size of 16, bucket size of 32. You can see here that the bucket size of 16 works very well in terms of performance or insertion rates. However, it does not achieve very high load factor. So it's around 0.85. Increasing the bucket size improves the load factor. However, it reduces the insertion rate, because now, instead of requiring a single cache line, you need to touch 2 cache lines to perform the insertion. So again, we have this trade-off between load factor and performance in terms of insertion rate or query rates. For positive queries, it's also similar. Here you can achieve very lower than 2 number of probes, because it is possible that you find the key in the first bucket and you terminate. So that's why the average number of probes goes down. But you can see here the same trend for the search throughput. For negative queries, again, this is like the worst case scenario for a query operation, because you need to touch the 2 buckets that you could have hashed into. So the number of probes is always going to be 2, because you're not going to find the key and you need to inspect the 2 hash function. And similarly, and like on the right, there's nothing new. It's just the same trend that we have seen before. For Iceberg hashing, it's similar trend, but the different thing here is threshold. So the threshold was basically how, like given a primary bucket, how much are you going to fill that primary bucket, up to what threshold? So these threshold are percentages, so it's 20% of the bucket size, 40% of the bucket size, and so on. So I would like to look at how changing the threshold improves performance. So for bucket size 32, between the red, blue, green, and purple lines, you can see here that as we increase the threshold, the performance improves. And the reason behind that is that you are letting more insertions hit in the first bucket or the primary bucket. So once you do more insertions in the primary bucket, you terminate earlier, and you don't have to check the other location, which, for example, could be 2. However, at higher load factor, you start to inspect more. You start to inspect these other choices. So remember, the number of probes was a number between 1 and 3. And on the right, you see the same trend here, increasing the number, increasing the threshold, improves the performance. And like here, for example, I think the best case was like the best threshold that I think we decided on was around 80%. For burst of queries, similar trends again. So I don't think anything new in this figure. For negative queries, I think this one is an interesting one again, because it's a worst case scenario for queries. And remember, we had 3 possible locations to hash into: primary bucket, 2 secondary buckets. And you can see here that you always have to do 3 probes to perform the negative query, because you will not find the key and you need to check the all possible locations, which are 3. And the performance in terms of search, we get similar, we get performance, the same trend, larger bucket size improves the load factor, but it reduces the rate that you can achieve. So across all of these implementation, the data structure that really outperforms everything else is bucketed Cuckoo hashing. So a bucketed Cuckoo hash table that uses a bucket size of 16, and in this case we use 3 hash function, outperforms everything else. You can use fewer than 2 hash functions, but like we saw earlier, it will affect performance in different ways. So the key take-home message from this figure is that a hash table that uses a Cuckoo hashing as its probing scheme outperforms all of these other alternatives. And yeah, finally, I'd like to thank all of the funding agencies, and I would like to thank Martin, Lars, and Alex for their technical feedback. And in the end, I would like to discuss a summary of this work and some ideas for future work. So again, the most important thing is how many probes you are going to perform. If we efficiently implement the hash table, and we can do that, we showed how to do that. The more once we have an efficient implementation, the most important thing is how many probes that you need to do. And we saw that bucketed techniques are very suitable for the GPU, and we would really like the bucket size to be 128 bytes. However, maybe for some techniques, for example, like Iceberg hashing, it requires a larger bucket for it to actually work, and you hit most of the time in the primary bucket. So you might be willing to sacrifice the throughput because you're increasing the bucket size and you're touching more cache lines, but you can get higher load factors. So there is this trade-off. And increasing the number of hash function, if you increase the hash function, you will improve the load factor. You will improve the insertion rates, and you will improve the query rates for positive queries. However, for negative queries, you will sacrifice the performance of negative queries, because the more hash functions that you use, the more buckets that you need to inspect when you are trying to find the key that does not exist in the hash table. And finally, we have choices. We have a lot of choices, as we have seen. So we shouldn't constrain ourselves to a single implementation. We have choices, and the workload should decide what hash table to use. Maybe I only care about positive queries, so I can use very large number of hash functions, and I don't care about negative queries because I'm not going to, because my workload does not perform negative queries. However, if your workload, for example, you expect a lot of negative queries, then you have to take that into account. So the message here, I think, is that we have a lot of choices and we should take advantage of the data structure and not just use a single hash table for all workloads that we have. And this is just a summary of the different techniques. And finally, for Iceberg, something that is future work for Iceberg, I think Iceberg hashing is a very powerful technique, and in fact, it works very well on the CPU, and it outperforms Cuckoo hashing on the CPU. However, the bucket size on the GPU is not large enough. 128 bytes for a bucket size or a bucket size of 16 is not large enough. So we would like to investigate how we can make this work for the GPU, because the idea behind it, it should work. Like the idea of optimizing for the common case, which it should work. However, we didn't get that right yet. So some ideas, for example, to achieve high load factor, I think that changing the secondary probing scheme will improve the achievable load factor. So instead of using a power of two hashing technique as your secondary hashing technique, then maybe you can use something else like double hashing or quadratic probing. So these will preserve the main property of Iceberg hashing, which is stability. And I think they will achieve higher load factor. And finally, we saw that for negative queries, for example, Iceberg hashing uses at least 3 hash functions to perform. It uses 3 hash function primary and multiple secondary hash functions. So we saw that in the worst case, you need to look into all of these possible places or possible buckets. So we would like to optimize the load factor. We would like to optimize the negative query performance. And an idea to optimize that is to use a quotient filter inside each bucket. So this will take space from our from the storage that we can store keys into, but it will improve the negative query performance. Again, if our workload cares about negative queries performance.